important thing is how you arrive at it. Okay, so now, so we started with this picture here, right? So the story is that we're gonna pick a notion of entropy that corresponds to some adversary of interest. Okay, so from this entropy, we're gonna transform it into some conditional entropy. So entropy measures uncertainty about the secret. The conditional entropy will measure the uncertainty that is left about the secret after assuming that we know the outcome of some other connected random variable. So from the entropy, we're gonna create this conditional entropy, and then in the end, we're gonna take the difference of the two, and this will be a notion of affiliation. So we did the first. Okay, this is the first part. We got our entropy. Now we want the conditional entropy. Okay, so the conditional entropy. Remember, there is this story of starting from a prior distribution here, and by doing Bayes' theorem, you end up with a posterior distribution. Okay, so this is the game we played with the matrix before. You start with the prior, and given an output, you get a posterior. And we're going to use this trick here to get a conditional entropy. So what we're going to do? So now I'm going to take conditional entropy of S given a specific observation. All right. So now, given that this big O is some small O, right? So given a specific, so I'm focusing on a specific observation here, right? And I want to measure the entropy. So what I'm going to do? Well, I'm going to just take the formula here. I'm going to create a posterior distribution based on this O from my prior distribution. And I'm going to measure not the entropy of the prior. So the prior is essentially what describes S, okay? So instead of plugging the P's of the prior here, I'm going to plug the conditional P's here, all right? And this is just as simple as that. I'm going to measure the entropy of the posterior distribution, okay? And this is going to be this formula, but again, the formula doesn't really matter. And now, of course, this focuses on a specific observation. I want an average case over all observations in my system. So I'm going to do exactly this. So the conditional entropy will be the expected value of the updated entropy, right? Given for all observations. I'm going to sum over all observations. I'm going to weight it with the probability, the marginal probability of the observation. I'm going to take the entropy, this updated version of the entropy, and this average sum that gives you in the end this big formula will be my conditional entropy. All right? So you see this interplay that prior I measure with an entropy, gives me posteriors. I measure them again with the entropy. I formulate this H there. So a priori I have this formula, a posteriori I have this posterior entropy, and then the leakage will be just the sum of the two. That in the case of Shannon is also known as mutual information, and will be my final quantity that describes how much I lose. So how much entropy I lose because of the system, right? So in the best case, that will be 0, meaning that I don't lose anything because of the system, right? So essentially, this does not necessarily mean that it's hard to guess my secret, but it's not easier because of my system. So my system didn't change anything, right? In the worst case, it will be equal to the entropy, and will mean that my system completely destroys the entropy of the secret. So before it was whatever it was, and now it became 0 because I revealed it. Then there are several properties that you can discuss about. So first is that the entropy that you start with is always higher than the one to begin with. So an observation can only decrease the entropy. In other words, an observation can only help the adversary, cannot somehow confuse the adversary, because you give more information, you cannot make things more difficult. So it will be the same or easier. Then, so the two entropies, the prior and the conditional, are the same if and only if the two events are independent. Okay? So if you think from the point of view of the channel matrix, this is the case if and only if all rows of the channel are the same. If you remember when we were looking at these dining cryptographers with fair coins, all the rows, it was very symmetric, this matrix, and all the rows were exactly the same. Okay? And remember that we were discussing that here that dining cryptographers have strong anonymity, right? There's really nothing that you learn, and this is exactly because of that. Because with fair coins, all the rows of the channel will be the same, and this will make the two variables independent, and this will make the entropy the same as the posterior entropy, which means that the leakage will be 0. Okay? So zero leakage corresponds to the strong anonymity in the sense of channel. But the good thing here is that it's not a black and white property. So it's not that either you have strong anonymity or you don't. You have anything in between. And then another important thing is that sometimes, so this notion depends on the prior information about my secret, all right? So depending on how well informed I was to begin with, the leakage might be smaller or bigger. So sometimes we want to abstract from that, and this brings us to what we call capacity. So the capacity will be just the maximum leakage. So I maximize this quantity here, overall prior, so the worst case leakage, right? This typical thing in security. If you don't know, so if I know what my prior is, I know that this user picks passwords with this, with respect to some pattern, okay, with respect to some probabilities, I'm going to use that. Otherwise, if I know nothing, then the safe thing to do is take the worst case, so maximize overall priors and distribute the capacity. Is this clear? Okay. So now we can run it. Visibilities. So, so very simple example here, so that it's easy to plot it. So I'm going to take 10 indicators, just 2 users. All right. So there's 2 users, and I'm going to assume that one of them will send a bit that's equal to 1. Right. So the input. So as we said we were doing before, so it has just 2 inputs and 2 outputs because just 2 users, okay? And, all right? So what we're gonna do here is, I'm gonna take a biased coin that, so if the coin is biased with 2/3 probability and 1/3 probability, it will give you this, this channel there, and then I can compute the numbers. But it's even more interesting if I plot the entropies as a function of how biased, no, sorry, this is not what I'm doing here. I might do this later. What I'm doing here is that I'm going to plot the entropies as a function of the prior. So I assume that the coins are always biased like this. So they give heads of probability 2/3 and tails of probability 1/3. So this is my channel. Okay, I'm going to change that. So what might change is the prior probability here, right? So what's the probability that the first guy, Frank, who even left because he could not stand me, calling him Frank, no, nothing. So, so this is, so I have a prior here that assigns P to Frank and 1 minus P to the other guy, all right? So I'm going to plot here. So this is, on this axis is the probability of Frank, okay? And I'm going to plot the entropy of the secret, so how uncertain I am about who is the sender, okay? And then the conditional entropy after the observation. Okay, the one will be this green line that is not very visible, but so it's somewhere there. All right, and this is the red line. Okay, and you can see first that so entropy has this convex shape. It's smaller. So the more I know about, so the more likely, the more far away from 1/2 any of the 2 users is, the lower the entropy, right? So in the one extreme that Frank has probability 1, the entropy is 0 because there's no uncertainty. I know that Frank did it. In the other extreme that the other guy has probability 1 and Frank has probability 0, again there's no uncertainty, right? So again I know for sure. So the higher uncertainty is in the case 1/2 here. Okay, so I look at entropy, the green curve here. And the highest uncertainty is in the case of uniform probability between Frank and the other guy, right? Here. And now the red, so the red, I'm doing this trick with the conditionals. I'm computing the conditional entropy, and I'm plotting this, right? And as you see, it's always less than the green, and strictly less, okay? Because this channel, because I took a biased coin. So the rows here are not the same. So there is leakage. Okay, the red value here, the conditional entropy, will always be strictly less, apart from the extreme cases of 0. It will always be strictly less than the prior entropy, right? So I always learn something about the system. And the difference between the two is the leakage. So the leakage, you can imagine it as the distance between the two values here. Right? And then in this particular example, it happens that the maximum leakage, which I call here capacity, right now to compute capacity, I have to go over all priors and figure out where is the greatest distance between the two curves, right? Here it happens. So coincidentally, it's not always the case, but it happens that the Shannon capacity is given in the case of, so the difference between the two is maximized on an input on a uniform input distribution. Right? This is not always the case for Shannon. Right. So this, get an idea of, and of course now if you want to look at specific numbers, so the numbers will tell you, how much more likely an adversary will be in guessing. And of course, already here you can see that, of course, this will be an approximation of the strategy because, you cannot learn something with 0.8 questions. You need one question, to learn something. It will be an approximation, but anyway. Right. All is good. So you get just the feelings of how this look like and why you have the shape and yeah, but of course an important thing is that security is a complicated and privacy in particular, they are complicated fields exactly because there's no single notion of adversary that we care about. Right? If you had a single guy that had a single goal and then we measured what he does, things would be simple. But often you have different kinds of attacks or different ways of measure these attacks, right? And this, by answering what kind of attack we care about and how we measure its success, this might lead to different kinds of notions. So in particular, that was the entropy. Okay. So, all right. People were using sound entropy because it has a long tradition, it's natural in communication, capture information theory. But then more recently, people started questioning whether this is a notion that makes sense or not, because it has some limitation. Okay, so in particular, sometimes you might think that the adversary has a limited number of attempts at this disposal, right? So this possibility of keep asking questions might not be natural, all the time. So sometimes the attacker, he has one attack to do, and if he can guess your secret and enters in your system, it's okay. Otherwise, he's say he loses. So in this case, this repeated situation doesn't make sense. But there are other situations. So I don't have time here to give specific examples. Is that so sometimes, although a secret might have high entropy, well, I can imagine a simple case. Right? So imagine a case where there's a single secret with high probability, and then a gazillion secrets with very low probability, right? So one element very high, a lot of elements very low probability, right? So this will have high or low entropy, intuitively. We have high entropy because although there is a single item that has high probability, the entropy says how many questions I need on average to figure out completely the secret, right? So okay, sometimes, half of the time I will start with a question with a strategy saying, I guess the high probability, okay. Half of the times I'm lucky, but then in the long, in the big set of other cases, I will need to do question because there are a billion different secrets with each with a small probability, okay. And this, you can imagine that this might be a problem in your system, all right? So if in your system, okay, on average, you need a lot of questions to figure out completely the secret, but half of the time you can guess it in one try. This might not be considered secure in your case, because half of the time the adversary right away.
I have a question, so
yeah.
I don't know how I should read this. Sorry. So the last thing, obviously. If it's very close together, everything, there is no best. Certainly, it's not a good strategy. Imagine there's just all these probabilities are very, very close together. then it's not complicated. It doesn't seem to me why it's obviously the best strategy.
So
what does it mean? I mean, what context? What is it?
Yeah, so I guess this was, so I meant it, to describe this situation where you have one element with high probability.
100 questions. Am I allowed 100 questions? Okay.
Yeah.
Then I don't think that this is obviously the best strategy, and there are other strategies which might be better.
So the best strategy, the point is, so the best strategy depends, of course, on how you measure your success, right? So what you want is that so you measure their success with the expected number of questions that you need to ask, okay? So you would like, if there is some cases that you can stop very, very quickly, right? You want them to have a high probability, right?
Yes, but if it's everything is almost the same, then it's just random choice. Then the best strategy, what you say, the best strategy.
Yeah, so this refers to this situation where one element has high probability and the others have small probability. Okay, so in this case, I mean, you should start with the one with high. I mean, the best case in any case, the best strategy is this, right? You need to split it. You need to split it. Anyway, I mean, the point I'm trying to make here is that, I mean, really, I don't care about what is the best strategy. I care that there are situations where an adversary might be able to guess your secret with high probability, okay, and still the entropy might be high, right? And this, in some situations, you might consider this to be, a bad thing. So if this is what you care about, if guessing your secret in one try is what you care about, then change the notion of attack, right? So now, if this is what we're interested in, we can go to one try attacks, in which the questions of the four, is the secret equal to something, right? So it's just one attack. There are no sets, so I need to pick an element, okay? And of course I can pick whatever I want, but the only thing I'm allowed to do is make a guess, right? And then the measure of success is how likely I am to make a correct guess, all right? And of course, a reasonable attacker will pick the secret with the highest probability, all right? Because now it's really clear. I just make one guess, and I win if I win if I guess it correctly. So I have no other guesses. Okay, so I mean now it is obvious, all right? So I guess this is where this obvious comes, like a way to prepare for this. So here it is obvious because I have just one guess, all right? All right, then I'm going to just take, so this is, so the max here comes from the fact that a reasonable attacker will choose the secret with the higher probability. The minus log doesn't really matter, it's just to convert this thing to a similar scale as I had before. And then, so this leads me to what's called Riemann entropy, which is just the minus log of the maximum probability of the error, right? So this corresponds to an adversary that just makes one guess, and the measure of success is how likely is this guess to be correct, right? Is it clear why this formula measures that? Right, because, I mean, the point is, I mean, if I want to guess something, I'm going to guess the thing with the highest probability, and this probability will be exactly that. Okay. All right. So, like in the case of standard entropy, this entropy is the highest when the distribution is uniform, and 0 when the distribution is a delta of Dirac, right? So this behaves in a similar way. Uniform distribution increases the entropy, because if I have a uniform distribution, then everything has so there's nothing with highest probability than the others, right? So my best guess cannot be informed at all. There's no real information in this probability distribution. So probability of success will be small, which will make the entropy high, because the entropy has this minus log here. So small probability of success means high entropy. When on the other hand, if there is a a delta point distribution that has probability 1 somewhere, then obviously we will make this guess. The probability of success will be 1, so the entropy is a minus log of 1, so it will be 0. Okay. Entropy, probability of success for the opposite way. All right. So now, okay. So what I want to do now is the second step, okay? So now I want to define a conditional mean entropy. Okay, so I start with an entropy for the prior case. So this is it. And similar to what I was doing with Shannon, then I want to do a conditional case, right? Except that things don't work exactly the same way as before. So remember in Shannon what I was doing is that I was taking this entropy, and with this entropy I was measuring a posterior distribution, right? So with the whole entropy here, I was measuring a conditional distribution, and then I was averaging over all observations. So if you do this here, it's not going to work. It's going to give you entropes that are negative, so this doesn't really matter. What I'm going to do is I'm going to play the same game, but with what's inside here, right? So essentially there's a clear relationship here between what's called base risk, which is the maximum probability of success, and the entropy, right? The one is the minus log of the other. So the minus log is what creates the problem here. So I'm going to just focus on the probability of success, which is this max here. And I'm going to do the same thing. So I'm going to play it in the, I'm going to focus on a specific observation, create the posterior, run the probability of success there. So here, instead of being the max of the prior, it will be the max of the posterior, right? So this will give me, so essentially this thing will give me what's the probability of guessing the secret if I know that the output is O, right? Okay, and this is crucial because knowing the output will change my probability, right? So remember that I'm making one guess, so I'm going to guess the thing with the highest probability, but the posterior maybe will have a different element with highest probability, right? So maybe it will be something different. Okay, so this is how likely I am to guess the secret when the output is this. So I'm going to take that, average it over all observations, and the result will be, well, I'm going to just define it like this. This is the average probability of guessing correctly the secret in all cases, right? And the end formula will be this. And now I'm going to just take the minus log of total, right? So remember here I was taking the minus log of this probability, creating the entropy, and now I will take the minus log of the posterior bias risk, and I will name this conditional mean entropy. Okay, so this will be a notion of uncertainty. We will quantify how likely I am to guess the secret after I know the value of the observation. Clear? So, I mean, the important thing here is to see like the difference between the one and the other. The nice thing here is this has a simpler, so more clear operational interpretation, which makes things easier to follow. Also makes the formula simpler, so these are considerably similar formulas as before. And again, to define linkage and just taking the difference between the two, so nothing more than this. And again, similar example, dynamic photographers, 2 users, biased coin. This is a channel exactly what I had before. All right, and now just the shape of these things changes. Okay, this is the shape of the prior mean entropy. All right, so again, the more skewed these distributions are, the more likely one of the 2 users is to send a message. The smaller the entropy, and the extreme case where one of the 2 guys has probability 1, then the entropy is 0 because I can always guess probability 1, right? And then the more we move towards the uniform prior, then the more the higher the entropy is, right? So the prior entropy is this green line here. It behaves similar to the previous case, just the shape is different. And now, now the posterior case is a bit more interesting here, because so again, similar to what was doing what was going on before. So when I start from 0 linkage here, and going up, Okay, increasing this probability, the conditional entropy here, of course, increases. Okay, but as you can see, it increases exactly in the same way as the prior. So that was not the same case that we had in Shannon. So here in Shannon, if you zoom in here, there's always a difference between the two, right? They're never the same. There's always some leakage. So remember, the leakage is the difference between the two, right? So here, so there's this, of course, there's the same shape overall in the sense that the more you move towards uniform distribution, the higher the uncertainty is. However, here there is absolutely no difference between the two, right? In other words, the system has no leakage, okay? Which might seem a bit counterintuitive at first because, okay, I mean, the two users produce observations with different probabilities. So when I see something, when I see 0, 1, well, this should tell me something about, so I mean, it does change my posterior distribution, right? If you look at distributions are always different. The only case for the prior and posterior distribution to be the same are the extreme cases. There's nothing else, right? So if I focus here on some, say, a prior that assigns 0.1 to Frank, let's focus here. This is a prior that assigns probably 0.1 to Frank and 0.9 to the other guy. Okay? If I look at the posterior distributions, they will be different, right? I mean, for sure, they will be different. But why we see that there is seemingly no leakage between the two? Because remember, the leakage here is measured as the success probability, right, of an attacker who makes the best guess. Okay? So the adversary will make the best guess that he can, and then the entropy measures the success of this guess in terms of probability, right? How likely was how likely he was to choose correctly. Okay? And now what happens here? If Frank has very small probability, so let's say it has 0.1. So imagine this happens, and we see this observation. Okay? So a priori I knew nothing. So if I was asked to make a guess, I will say that Frank was not guilty. Right? Sounds unlikely, but no. Given this probability, this is what one would say, right? So Frank has small probability, so I'm guessing for the other thing. Now I see this observation. I know that this observation is produced by Frank with higher probability than by the other guy. So this gives me evidence to support Frank, right? However, Frank had very small probability to begin with. Okay, so maybe the posterior probability, okay, Frank started with 0.1, maybe now it's 0.2. But still, the other guy has more mass by himself, right? So even, essentially, Frank was so unlikely to begin with that even when evidence came to me, I still believe that, okay, it's more likely that the other guy was the sender, and then it just happened that he produced the less observable event than that Frank was. I mean, so there is some evidence, but the event is so unlikely that the evidence is not enough to make me change my mind. So essentially, now a posteriori, because the evidence is not good enough, I'm going to still guess the other guy. So it doesn't change, I don't change my mind, essentially. And because I don't change my mind, my probability of success will be exactly the same. And it will be 0.9, the probability. So I'm going to choose the other guy, and I'm going to succeed with probability 0.9. Okay? So, and essentially, so you see that although I have some good probability of success, the system didn't produce any difference. Right? Because the system was not enough to make me change my guess. And the only thing I care in the mean entropy world is about my guess and how likely it is to be correct. In all these cases here, right, there's no leakage, essentially. This system is with this attacker is perfect. But of course, there's a tipping point as Frank's probability increases. Right, there's a tipping point that the evidence here will make me change my mind. Right, there will be a point here around. Maybe, I don't know what the exact number will be in this case. Maybe 1/3, I guess. Yeah. Quite likely. That now when I see the evidence, right? Before Frank was less likely, but now the evidence, make Frank more likely. So now after the observation, I change my mind and I'm more informed than I was before. There are some cases where, without any information, I would choose the other guy, but now I have information about Frank and I'm gonna pick him. So here I have this plateau, because essentially, no matter where I am in here, the observation will help me in some cases, so I will have probability 2/3 to be correct always. Right? And then on the other side, it's similar. And of course, the leakage will be here I will have 0 leakage, here I will have non-zero leakage, and the worst case will be in a uniform probability. Right? So one thing to note here, it's okay. So the differences with respect to Shannon is the shape, of course, the numbers, the fact that you have 0 leakage when in some cases, right? In non-extreme cases. And the other thing to note is that, so here, in the case of Shannon, it was just a coincidence of a specific example that the maximum capacity, so you can say that the capacity, the maximum difference between the two is in the middle, right? In the case of Shannon, it was just a coincidence. I can construct different examples where the shape is a bit shifted to one side or the other side, and will make the capacity be given in a non-uniform distribution, right? So it's not always the case. While here it's always the case. So no matter what example I take, here the capacity will be given by uniform probability. And this is also a nice feature because it makes it easier to compute. So capacity is always an upper bound on leakage. So if I can compute capacity more easily because I know which distribution is given from, then things are easier. So properties, in general, leakage is non-negative, and I mean for all entropies that I'm using, I would like to have this because I mean a negative leakage would be counterintuitive in the sense that it will make an adversary being less capable, less informed after an observation than he was before, right? And this intuitively is absurd. I mean, an adversary will just ignore the observation if no use. So this cannot be confused. Alright, so if all rows are the same, the leakage is 0, okay? But we saw that in contrast to Shannon, not vice versa. So to have, if all rows are the same, if I have this strong anonymity property, then the leakage is always 0. But it's not necessarily. Okay, so it could be that I have 0 leakage without all rows being the same. For instance, here. So here the rows are not the same, and for some priors, the leakage is 0. Okay? Now what about capacity? So capacity, remember, is the maximization of leakage over all priors. Some properties. So now for capacity, the even only if holds. Okay? So if the rows are the same, capacity will be 0. But if capacity will be 0, it's an even only if. If capacity is 0, I know that I have strong anonymity. So it cannot be, so here it happens for some priors that the leakage is 0, but not for all. If the two shapes coincided for all priors, then it should be the case that the rows here are equal. Okay, and not only that, but capacity, so not only I know which distribution is given, but because of that, I have a direct formula for computing it. So the capacity is the log of the sum of the maximum of each column. So it's enough, if enough to go to each column, take the maximum value, so the maximum of this column is 2/3, the maximum here is 2/3, I add them together, and I get the log of that, and this will give me the maximum capacity, so the distance between these two things, right? The log of the sum of the maximum of each column. Another interesting property, in the deterministic case, so if the channel is deterministic, the Shannon capacity and the mean capacity coincide. They're exactly the same, right? But this is not true in general. Another interesting thing is that so mean capacity on the other hand is always an upper bound in Shannon capacity. Okay, so which is useful because this is easy to compute. Okay, this is harder to compute, and it's an upper bound. So if I compute that, even if I don't care about mean entropy in particular, if I show that it's small, then I know that also Shannon capacity will be small, so I can indirectly provide a bound for the Shannon capacity. Right? So maybe entropy, on the one side, it's a like natural notion, correspond to a natural adversary. So we might actually care about this, or the simplicity and the fact that capacity is computed easily might just be used as a tool to provide a bound. Yeah. It's also, we'll see a bit later that it's a bound for lots of other notions of leakage, so it's a good bound in general. How much more time? It's okay. All right. So just to see how these things work out, let's do a small little proof to see to prove these things. So why the capacity is obtained on the uniform distributions, and why it's the sum of the max of each column, right? So how does it work? So I want to prove that this is bounded by the log of the max of each column, right? Which is that. So how is this defined? This is defined as the entropy, the prior entropy. So this is leakage, okay? So this mean entropy leakage. Standard formula is the prior minus the posterior. Okay, so the prior is this, minus log of this max. Okay, and then the posterior is this is this formula here that came from this formula, right? So it came from this for this conditional Bayes risk averaged over all observations that gave me this formula. So I apply it there. So this is conditional entropy. Now I'm using the fact of how log behaves. This will be the log of these two things. Another interesting thing here is that, so I have a maximization of the product of two quantities, right? And these quantities are positive and non-negative, basically. So the maximum of the product will be, so this is maximum over or less, all right? So it's the maximum of a big set of products like that, okay? So now if I maximize each element of the product independently, right? So necessarily the what I get will be bigger, right? So instead of, so I maximize, it's a quantity here that's maximized together, right? And here I maximize each one of them independently. So it cannot be smaller, because if, I mean, if this was smaller than that, then I could, I mean, I could pick in principle the same as here and there, right? But not necessarily. Okay. So this is necessarily bigger. So then on the one side I have this that goes away with that, and I guess just you see it's a simple proof. So this is why entropy is always bounded by the log of the sum of the maximum of the columns, right? And now, small exercises, you can verify that this is given by the uniform distribution. So you can just take the formula here, plug a uniform distribution where each one of these things is 1 over n, and you will see that you end up with the same formula, right? So this is, so first it's a bound on the leakage. So this quantity here is a bound on the leakage, and it's also achieved on a uniform distribution. So it's a strict bound, so it's exactly capacity. All right. Let's see. Okay, a couple more properties. So, yeah, this discussed already. So the entropies, both entropies are 0, if and only if this is a point distribution. It's easy to prove. Now the maximum value of both is the log of the number of secrets. Okay, so it's maximized on a point probability distribution, and on that distribution, the value of both entropies is exactly the log of the number of secrets. Some mutual information is symmetric. So if you sort of try to see a channel from secret to observation, you bring it around. So you look at it as a channel from observation to secret. Doesn't make much sense in this application, but it makes a lot of sense in information theory. Then you will get the same result.
Even in the deterministic case? Even in the deterministic case?
Yes, in the case. Yeah, this doesn't.
Doesn't matter.
Does not. In particular, if the channel is deterministic, then the mutual information will be the same as the entropy of the output random variable. So you can just look at variables, at our outputs as a random variable, and the mutual information will be this. And then again, if the channel is deterministic, complete the capacity is very simple. Just look at the number of different observations of your system, right? And this is exactly your capacity. This is the maximum possible leakage you can have under both Shannon and mean entropy, right? So deterministic systems are easier, and you just need to count the number of outputs, right? So going back to the password examples, for instance, that are deterministic. Okay, so immediately from this, you can tell that the first example that was the password checking program that did not stop on the first bit has only 2 observations because the timing is the same always, right? So here you have just log of 2, while in the other example you have more different observations, so necessarily the capacity will be bigger, right? So this directly you can see why the one is better than the other. All right, and then so there's not much time. In this lecture, it's only 3 lectures. I'm not going to do exercises during the course, but in case you're interested, you could try proving some properties like why this thing is not negative, or why if the rows of the channel are equal, this is 0, and so on. So if you're interested, then you can. There's some simple things that you can try out. This will be a natural place to start.
Okay, so we're going to the break. Kostas will continue his tutorial tomorrow at 8:30. No, 2:30. 2:30. Okay.
And Pavel Sokoczynski will be in the usual, in the morning, 8:30. Right. Talking about graphical linear algebra.
Okay, so we'll go back at the 4:30, please. Right?
Next is Martin Lutker.